Assalamualaikum. In this video we're going to learn about the basic mathematics, basically like the linear algebra stuffs, right? Not deeply about the mathematics. I'm not that much of interested to talk about it because there are lots of good resources where you can actually learn some good stuffs, right? I'll just share those links, or you can just share those links as well. But my main concept for this video is that you need to know like what are the things or where do we use machine learning, and what's the connection between mathematics and the machine learning, right? So this is how things will work. Okay, so first of all, what we are going to talk about is linear algebra. Okay, so linear then algebra, right? Great. Okay, so linear algebra is basically a branch of mathematics which basically focuses on the study of vector, and there are other few stuffs like the vector spaces. Also you can call it as linear spaces, linear transformation, linear transformation, great, and system of linear equations. I believe you have been by now, you have worked with lots of linear equations, so yeah, these kind of things. And it provides a framework for understanding the properties and operations of these mathematical objects we have been talking about, right? Now you may ask, like, how is it like how do we use linear algebra, or what's the connection? We'll just learn it gradually, but first of all we'll also introduce like the things like vector and matrix and so on, right? Great. Okay, now talking about the other things, first of all, let's just understand a brief of like, okay, how things are working. Okay, so first of all, okay, let me give you some examples, right? Okay, so one should be linear algebra is used in basically you can call this model training, right? Now great, what is this model training and all, right? Okay, so what's this model and what kind of things it is, first of all, right? So in general, this is something we need to keep in mind, that is a model is basically assume that as a black box for now, right? Black box. So, and just for the black box, great. Now what we are assuming is this is a black box. What we do is we just provide some sort of input out here. Okay, we just provide some sort of input out here, and we just then get some sort of output from this, right? Okay, so we have been using machine learning in research for a while, right? So if you just research, or if you want to do research on machine learning, first of all you should know these basic things like vector and others, and this kind of stuffs. And the reason is why they're just talking about linear regression. If you just talk about a linear regression, if we just draw this out, I believe increase this a bit. Okay, linear regression, right? Let me just make it black, I believe. Okay, I'm not sure, sorry for that. Great. Okay, so assume that this is like our x-axis and this is our y-axis. Okay, and within, like, you can call it two-dimensional, right? 2D, obviously 2D, right? So within that we can plot some data, and now data can be for like maybe a for the house rent. It can happen, right? Like for example, you want to choose a house, or you want to buy a house, and there can be lots of metrics for that. Maybe the matrices are some sort of area of the house. It can happen, right? Sorry for that. Okay, it can be the area of the house, area, it can be number of rooms you have, then it can depend on the location as well, right? Isn't it? And the location, okay, and depending on that, we just have I believe we just have the amount, right? Like how much we need to put, how we need to buy a house, right? This is how things will work. And these things now, due to like I don't have the space here, okay, let me just this, and we'll just write it here. Great, it is not a big issue. Okay, let me just write it here. Area, and then number of rooms. Great, then the location, and then depending on that we just have this amount. Okay, now the thing is the area can be 1,200 square feet and so on. Number of rooms can be maybe 3. Location can be something. Now the thing is this location is again something we can use some numeric data here for example, if you look for Dhaka, we are just for example we are assuming Dhaka is the location code for Dhaka is 1. For others, maybe for Chittagong it is 2, something like that. So maybe in Dhaka this location is 1. Now the price should be 1 crores. So yeah, something like that, 1 crore Taka, right? Something like that. So or we just assuming that yeah, CR, we're talking about them in CR, no problem, we're just using 1, right? Great. Now you see all of the things, the whole data, whatever we had, we've just presented them via data, right? Now what happens like when we have for example I've been provided is 700 square feet of area, and the room is 2, the location is 2 as well. What should be the amount, right? Now here in this thing, if we just select, right, okay, this area, number of rows, locations, these like these are something depending on these variables, we can call some sort of variables, independent dependent ones. Depending on these, we're getting something, right? So this amount is actually depending on all of the 3. Maybe it can happen that is like you've been said like okay, the location is not a something you need to worry about, right? So maybe we're not worried about the location, we're just worried about area and number of rooms. Maybe that can happen, but in general it doesn't, right? Depending on the city, the obviously the amount varies, right? So but this is how things do work, right? So now what we do is, in general what we do is we are just basically plotting this data, and depending on that we're just guessing where should the amount be, right? This is how things do work. Now for example we just take these two, area and amount, right? If you just look into these two, and if you just like this thing, so for example this is our 1,200 square feet, and this is 1, right? Sorry, this is 0, this is 1, right? Okay, this is 1, and this is how things will work. And if you just look into, just assuming the amount depends only on the area, okay, we are just assuming this, and it makes this graph a 2D because we have two information. One is this amount, and another one is we have the area, right? So now the thing is, if we have obviously 1,200, and if we have like for example it can be something like that, maybe 700, right? So why should we get this point, like get the amount, like it's a point something like that? So we basically do the mathematics and others, and we just do find out like okay, how do we do that, right? In linear regression, now you see like if they follow the same trend, we have some sort of equation called y equal to mx plus c, right? So this kind of equations basically, like when we do is kind of this kind of thing. So what happens is that, like, maybe this is a point, maybe just assume it's 2 and 3. Yeah, I'm not verifying the data. Now what happens is, like, we know the M, we know where the C is. This is where the C, the value of this is C, right? Okay, now depending on these, like, if we are provided, just understand, if we have for example, y2 3xy, okay, this is 3 and x is 2, and depending, and we also have got somehow have got the value of M, or have been provided, whatever it is. We can use multiple equations to get that is also some sort of way. So assume that we have been provided M, and we also have been provided C. Now what is left, right? We can just easily see, like, okay, we can verify, okay, is this so, can we get this one also? That's good, no problem with that. Now what if we don't have this one, right? We don't have, oh sorry, my bad. What if we don't have this one, right? Y, but we have been provided X, which is 700. We can just get that, right? 700. So now using M, X plus C, we can easily get the value of Y. And this is how we will get the value of Y here. Maybe somewhere near here, maybe 0.75 CR, right? This can happen. So this is how you can see it's a simple linear regression, and it's part of linear algebra, right? So using that, there are lots of projects. You will see there are lots of beginner projects. You might see that this is how these are created. Now talking about these things, we just need to understand another important factor, and that is how the data is represented. Okay, for example, let's talk about this, like, okay, yeah, I was talking about the location, right? It can be 1 or 2. Okay, so here you see, when we were just talking about let's just forget about this one. This is our Y, right? And this is X. We're just much more motivated right now to know about the data, input data, okay? Because we know, or you understand, like, okay, just understand, like, now understand the black box as M and C. Okay, why am I saying that? Because we are providing X and we're getting Y, isn't it, right? This black box is M and C, because there's the equation. Basically the equation is Y equal to mx plus C, and somehow it gets the value of M and C. There are lots of things, lots of various way, and that can be used to get M and C. Okay, but you just don't need to understand, just we are understanding it for the beginners. Like, for example, we now have M and C somehow, and every time we get an X, we just get an Y, right? Now we just need to also understand, like, how the data is represented or something. Now here is one thing. You see, we had area of 1200 square feet, and if only we provide this information, just I have used that, sorry for that, 1200 square feet, we are just getting, maybe we can get a value of Y. But if we just pass this one, we can call it in 1D. Okay, 1D, one dimension. You see, one dimension, because if you just put it like that in a graph or something, maybe in 100 200, you can just check that, okay, this, the whole value consists of 1200. It's just one dimension, right? Now if we consider to take these two, like for this example we have taken just one, right? One input. But if you want to take these two, we have to use like this. 200, I believe, is 3. Okay, great. Okay, we're just passing this, and this will be called some sort of 2D data, 2D dimension. And like, this is how things will work, right? 2 dimension of input, we're just passing that, and we are not currently bothered about Y. But if we want to pass all of the 3, what it should be something around 1200, 3, and maybe 1, right? And it's a 3D data, and this is how things will work. A 2D data should be something like this, and there may be 1200, there might be 2, and within that this is our point, right? Let's say 2D, right? 2D point, and for 3D is something like, right, and the data should be somewhere here. Okay, so 3D one. Okay, great. So from here or something. Okay, 3D, great. This is how we are actually working with the input. Now we just understand, like, okay, this kind of this is how the dimension and things are going to appear. You just don't need to understand a lot of these things, but whatever, like, most of the time what happens is, like, you can visualize 3D data, but you can't visualize 4D data. Like, there are lots of limitations. So what happens when we have more than 3D and or a lots of dimension, lots of inputs, what we do is we reduce the dimensionality. For example, there are some sort of algorithms called PCA and others, which will actually, like, take you, like, maybe for example you have a 4D input, it will take this input to 3D. Now you can ask, like, okay, how is it possible? Is again our linear algebra where we're going to learn about it, because for example, you have a matrix called maybe matrix, you have a value. For example, you have a value of, like, 40, right? Or just, you can use it like this way, or you can also use this way as well, as a column matrix as well. No problem with that. It's a row matrix, right? If you don't know about matrix, we'll just talk about it within a while. Now talking about, like, for example, you have a value of 1200, 3, 1, 2, right? So using some sort of matrix multiplication or other, maybe there are some sort of value or whatever it is, we can get, like, maybe for example you can get 1200, 3, 1. Not exactly the same value, but it will be different, for example, for sure. So I should be using a different data for sure. It can be maybe 750, 1.5, 0.8 or something like that. Now this is not exactly how the data should look like, but again, this is something like the dimensionality has been reduced. You see, there are now currently, it was 4D, but it's currently 3D. So there are less dimensions, less inputs, but the main motive remains is that we want to keep the variance. And what is variance? Is basically the patterns and the relationships. We want to keep that, and depending on that, we just want to get a new input. This is how things do work. Okay, let's not make it complex much more. Okay, now we'll talk about we have talked about where we use the more linear algebra. First of all, it was in model training, great. Then we have also talked about, like, in the dimensionality reduction, we use that, and it's basically the PCA and others. And in PCA we basically use eigenvectors, so eigenvalue vectors, etc., and we'll talk about it later on. Again, we use them in our neural networks. Okay, currently, if you have heard about the LLM and others, it's basically deep learning, and you have to learn about deep learning if you want to research in machine learning. So in neural networks, we basically have something like that, maybe some sort of neurons, these kind of things. We're just passing some sort of input, and after that, within that, we have lots of others neurons, and it just goes through these, and there is some sort of mathematical stuff that happens, and so on, lots of things that happens, and after that we get a result. Okay, for example, we may pass like, okay, some sort of the training data for maybe dog. This is dog and this is cat, something. It is we have just passing the images of dog and cats to some sort of model, okay, neural network, and it will learn from it the patterns and others, and later on we can just verify from it, like, okay, if an image is dog or cat or so, we can just do that. Okay, later on, just it was just for an example, but this is how things to work. Okay, now what happens here is there's something called weight. Okay, it can be like weight 2, weight 3, weight 4, something like that. Now what happens is we're passing some sort of, like assuming f1 f2, so there is something like f1 f2. We're just multiplying it with all of the things we have currently. I am not sure if I have created all of the probable one. 1 2, oh, I missed one. The connections 3 1 2, and it should be 3. Okay, so I believe I missed this once. So just 1 3 4, that kind of w, sorry. I am just renaming it as, just don't need to focus that much. We're just renaming it, like, okay, there's a connection for, it can be w6 or something. Okay, so we have w1 w2 w3 and w4 5 w6. Great. And this is basically a matrix multiplication what we do here, and we are basically doing that, this multiplication and passing the data to here. This is how things do work. There are some things called forward and backward propagation. So this is how things work. This is the data goes through the forward propagation, and the multiplication is done here. And later on what happens is there is something like cost function which is associated with it. Cost functions mean, if you know about it, cost functions main responsibility is to check, like for example, we're expecting you're passing dog and cat's data, right? And you're expecting the data should be maybe when it is a dog, it should be dog, right? But maybe it is detecting a cat, right? Now the cost is to understand, like, if this is something, it has detected it properly or not. For example, assume that we are passing 2 and 3, and no, it's not relevant, but we make some examples. Okay, what can we do? Okay, the dog and cat should be better. Okay, we're just passing the dog and cat data, and something like that. When the data is like, maybe we have 70 dogs images and 30 cat images, so we're passing that. So the model is learning from it, and it is expecting, like, when you're passing a dog data, you're expecting the data, the result should be, or when you are just training, there are two phases in machine learning. What happens is, first of all, what we do is, like for example, this is a model. We just, in neural network, it is not neural network, it's just basically the basic stuff, like, okay, we are putting some input and this is the model, and you're getting some output. But here's another thing, in the neural networks, it's quite different. Neural network is, you will see, you have lots of neurons and all these are so much connected, you will see that something like that, and we get some sort of this kind of things. Okay, great. This is how things do work. So what this neuron does is, or what it is used is basically for, maybe for assuming that you are using it for binary classification. And so what is binary classification? For example, you have dog data of 70 dog data, and you have cats data, 30 images, 70 and 30 images. Now this is great, right? 70 and 30. Now if I provide like a dog's image and want to ask, like, hey, can you detect if this is dog or cat, I'm expecting it to get, like, okay, yeah, it's a dog. When I'm providing a cat image, I'm expecting it to get cat, right? So dog and cat's images, we're passing it to neural network. Basically it's called something like convolutional neural network, CNN and others. So the images are not surely good, but the neurons, I can just make it better, no problem with that. Better, but it basically learns from the patterns. Okay, like from the dog's images. If you just check an image, or if you have done any kind of computer I would say design or this kind of architectural courses, you will see like any image is basically a full pixels, right? There are lots of pixels, and basically they have some value, and depending on that we just get an image, right? So like that. It's just assuming 2 3 4. Just it's not realistic. I'm just making it some sort of neurons and others so that it's looks okay. Okay, just like that, no problem with that. Just assume that CNN and others. So like, okay, dog and cat and others, so it basically learns from the patterns, and so on. Now there are a lot of times what happens, it can't learn properly, so there's something called cost function. What happens is it basically finds out like, okay, are you learning it properly, are you getting it right? So if you're not getting it right, what happens is it's basically, once we were doing the forward propagation, the multiplication and others, then the data is passed again and we do a backward propagation, and we what happens is the value of the weights are changed. Okay, but weights are changed so that we can get the desired data. So these kind of things you will learn later on. If you learn, I have written lots of blogs about it, but you can just learn about it, right? And as I was talking, these images are basically some sort of part of the computer graphics. So if you have just worked with it, it's great. The graphics and images you see, sorry, okay, these are some sort of images, and these are kind of, we have lots of pixels and so on, right? Great. And we have lots of we have RGB, like basically they are called the 3 channels, depending on that 3 channels. So yeah, some sort of things. So you can just create this one, and 3 channels depending on that. Yeah, so one might be for R, one might be for G, green, and one might be for blue, and depending on the, you just get some good images. So how things work. And also for the optimizations, we do use linear algebra, right? For example, I was talking about y equal to mx plus c, right? I was talking about y equal to mx plus c. So isn't it something I mentioned, like we can somehow get m and c, right? But it is very important to get the best or the best value, or the correct m and c, right? For example, you have been provided like for 3 equal to what can we give it? If I just provide the equation like 2x plus 9, and I don't know if this is realistic, 9 equal to 2x plus 4 or something like that. It's not like we're just getting the value of x and something. You can easily get it from here, we just easily get it from here, so on. But it's not the problem. The problem is we need to, I bet this should not be good example. Okay, for example, assume that this is given 3 equal to m 2 plus c, right? And again 4 equal to m 4 plus c. Now from these two we can easily, if we just minus, like from this equation, equation 1 minus equation 2, so we can easily get minus 1 equal minus 2m, right? And we get m equal to 1 by 2. It's half, right? This is how we are getting it, right? This is just for the two equations, but what if we have like thousands, right? What if we have thousands, and then, or what if we have hundreds, right? There are a lot of techniques like gradient descent and others which we use to get the best m and c. Okay, best m and c. And also, if you want to visualize that, it can be something like this. For example, there are lots of graphs, like lots of linear lines we have. For example, this kind of things, lots of linear lines. And using the linear, so the gradient descent, there is some sort of algo. We have to find the best m and c. Maybe this is the best m and c value, and we then get the m and c value. Okay, so this is the optimization. We are trying our best to get the best value, and we use basically gradient descent. It's again part of mathematics. Great. Now that's a good thing, right? Now talking about vectors, let's start something about vectors. Okay, great. Vector in general, the vectors we do say, like if something has value and a sign or something, it's a vector. But in the mathematics, we don't just say like, okay, if something has a value and a sign, it's a vector. In when you were in your class 19 or 11, 12 in Bangladesh, maybe you just learned like, maybe if something is within our 2D, maybe if something is like this, maybe 2i or something, it can be called as, okay, surely it's not 2i, like I should be here, but 2i maybe plus 3j or something, whatever it is, something like that. It's a vector. You just learned about it. But in mathematics, or if you talk about the machine learning, we just don't say that. We basically use something like the matrices to represent vector. So how to understand like what is a vector? For example, assume that you have a course, maybe it's called computer science 340, okay, computer architecture course or something like that. Now now the thing is, it's said like, okay, you have got, for example, the marks, okay, for marks, like this student one got 90, and number of study, or like for that the student studied for like maybe 3 hours daily, great. And we're just saying, okay, did he or she passed or failed? It's like passed, right? And again another student got 40, and the study hour was 1 hour or something, and the student failed. 40 is something, maybe assuming the 50 is the passing mark, okay. And now here a vector representing like the person's marks and number of study, the marks and the number of study, okay, here you can see. So it's not just representing like we have just learned about it earlier as well, like the 2D data, right? It's a 2D data, all right. But here we're just not learning about the data, we're just also learning this 90 is basically mark of this student, and this 3 is basically hours of study, right? So it's representing data as well as something information more. It's basically like the earlier definitions of like value and sign or something, but right now it's not sign, it's basically some sort of, you can call it as more information, right? Or the real information. Okay, so this is how things do work, right? Okay, that should be great. And now what can we learn? Okay, in reality, like if we want to understand how the data can be how the data works, for this example at least, just understand this from here. If what we just understand of, if we just guess it like f1, this can be, or f2, no problem, and this can be our fail or pass, right? Great, no problem with that. We are assuming pass as 1 and we are assuming fail as 0, no problem, right? We can just get that just like the Dhaka, we assign Dhaka as 1 and Chattogram as like 2, right? We can just assign values, right? We can just do that, we can just understand, because this is how things will work in general in the machine learning. You will see that. Now if you just plot the data, what happens is first of all, for the 90 and 3, right, this for 90 and 3, and I'm just giving it should be something, it's better to have greenish something, right? I'm not sure if this, yeah, we have just passed, so it is great, right? Great. And for 40 and 1, this is 40 and this is 1, and it should be something we can use the reddish one, right? Okay, great. Now this is how, now we just had two information, right? Now we may have lots of information and so on. Now I'm just trying to plot I'm just trying to add more data, right? Here, for example, past, first, you will see like the lots of data you are inputting and you are getting this. Just assume that we are getting that, and this point, this point, this point, and this point, something like that. So after a while, 1 2 3 4 5 6 data, 7 8 9 10 11 12 data. We have 12 more data, like 10 more data. Like after this we just had 2, and we just had more data, right? Something like that. Great. So after a while you can just easily understand, like for example, you can see there is a line out here, right? Can't you? You can see there is a I'm making mistake. Okay, the line should be something like that, right? You can see a line, right? You see all of the students who have passed are actually above the line, and all of the students who have failed are below the line, and this line is basically nothing else than mx plus c, right? You are basically working with the vectors, and you are again talking about the linear algebra out here. So these are the students who failed. Now for example, if anyone say, like for example, you have been given like what should be the result of a student who got 70 and studied like 2.5 hours, okay? Like it was for example it was 90, something like that, so it should be 70 and 2.5, maybe just assume that this point or something. Now you see it is above the line, so we can say the person actually passed the exam. Great, he or she passed the exam. Passed. So from this equation we can do that. So this is how these things do work. I'm not trying to like talk much more about okay how the things do work or how the maths do work. The thing is how we use mathematics and in machine learning. This is how I want to show, okay? This is how things work. So talking about these things, you will learn about the vectors and others. Vectors are mostly used in lots of things, right? It's used in lots of stuffs. One of those are, you can call it, first of all, is word embedding systems. Like for example, you have some sort of data for example, we have a word called data, right? And you can represent this word, sorry, maybe making it black should be better. Oh, it's not black yet. Sorry for that. Oh, I have to choose it from here, my bad. For example, we're just talking about the word case. First of all, word embedding, okay? Word embedding, like okay, for example, so we have some sort of text called data, and we can represent this via some sort of vector. Like for example, it can be represented by 0.2, sorry, 0.2, 0.1 and 0.4 for something like that. And then we have some sort of other data as well. It's called size. Maybe the size can be somehow represented as 0.3, 0.7, 0.2. Great. And now if we want to know what should the value for the word called data science, what do we do? If we have learned about how to actually add vectors, you can easily understand how we do it. So I'm assuming you know about it, how to add vectors. So it's simply like 0.2 and 0.3. We just add those up, 0.5, 0.8. We're just adding those 0.4 and 0.2, 0.6. So the word data science basically will have the value this is how we are using the word embedding, and it's basically using the vector add. or addition. Simple as that. Now talking about others, we have like for image processing, we also do that. For the image, for example, talking about image processing, right? So for the image processing, for example, any color can be represented like this, RGB, okay, in the R, G and B format. R has some value, G has some value, B has some value. If we have a red color, what happens is the value of R becomes 255, okay, and the other, it is not directly 0, it's like something like 128, and the blue is 0. And for green, it is something again RGB, right? So if we are choosing this one, it should be 128. G is green, it should be 255, and the blue can be 0, right? So this is how things do work. And also for the blue, it should be 64, 64 and 255. This is a lot of things that happens. But for now, why am I talking about it? Just let me just write down blue. We can call it like 65, and it can be 255. Now, why am I talking about this thing? Like, why do we need to know about it? What happens is sometimes, and you will see if you're working with convolutional neural networks or if you're working with the image processing, what you will do, because there sometimes you will have colored images. So working with colored images is tough because the value, the lot of things you have to deal with. So what happens is we just make it grayscaled. So from RGB we make it grayscaled, okay, grayscale data. And a grayscale data is basically we just add all of the data, and like for example, we had this was basically, it's not like red, green and blue in general. For red we do have this. It was basically for an example of data. For example, we just said 3D, right? I'm just writing it wrong, but I have nothing to do. Basically it's maybe R, it's maybe green and RGB. So for this image, particular image, this is the R value, right? This is for the green and this is for the blue. And in general, this is how things do things are represented. For in the R you will see R plane, this was the value, and in the G plane, this is the value, and this is blue. And what we do is we just sum all of these. So what we do for the RGB, and we just sum all of these, so it will be something like 255 plus 128 plus 65. It's for the R, and then we just sum all of the G value and then sum all of the B value, and we get something like 149, 49, 85 or something. We get a new value, and it's a grayscale image, okay? So this is how we turned a three-dimensional image like we had earlier, and every time you see the red had some sort of value, green or some, and we just have made it easy for us right now. 3D, from 3D to this, right? This is how we will work with our lots of stuff. And also we have in vector, we have dot product, we have and we have cross product as well, right? I believe you know about it. And dot product is basically just a multiplication, the normal multiplication of vectors, okay? We just talk about let me just make it dot product is basically something like, okay, we have this vector and we have another vector. For example, we have 2 and we have 3 and we have 4 and we have 5, okay? And what we do, if this is A and this is B, if we are looking for AB, what we get is we are getting 2 into 4 plus 3 into 5 is easy, right? We're getting 23. Is something scalar value, because you see it is some sort of vector, but right now this is not a vector. This is some sort of scalar value, just one dimensional data. It has been changed, right? And it's very easy. But talking about the other things like the cross and others we do, right? You'll see lots of things we do learn from it. Now, there are very much like implementations, the various implementations for this kind of things. For example, if we talk about the cosine similarity, right? If we talk about this one, we can also, this is easily just the multiplication dot product, there's no problem with that. But there's another rule called like for the vector multiplication, we just basically do AB equal to A B and cos theta. So using that we can also do that, and using that, or using the, if you just want to get the cos value, you can just get from AB divided by these two, right? And this is basically used in RAG. Okay, so in the generative AI apps, what we do is basically something we want to find the similarity. Like for example, someone has created something using AI, so our target is to get the similarity, like okay, is it something that's very near. We train on the AI generative data and we want to just find like, okay, is it AI generated or not? We're trying our best, right? So this is how things do work, right? Okay, great. Now what can we learn more? Interestingly, we should be learning much more about other stuff, right? Like after vector, we can just use or talk about matrices, right? Great, let's start talking about matrices, but keep it in mind that there are lots of implementation of vectors. We have talked about only a few. For example, we can use that in the recommended systems, right? For example, if you just look into the recommended systems, if you just assume that prior to that matrices, just understand for the vector part, again we will start vector because matrix has so much similarity between with vector, we can just easily understand that, there's no problem with that. But for example, that assume that from Netflix you are watching a movie, and it might be Avengers, I'm not sure it's available on Netflix or not. It Avengers, and Netflix has some sort of value for the movie, maybe 1 2 0 3 1. And why? And what are these values? Maybe 1 for the action, 2 for the comedy or something, the 0 for drama. I'm sure that this should not be some sort of this is not how they are actually doing it. Obviously this should not be the value, like the drama should not be 0, right? Okay, and 3 maybe for the romance, and C maybe for the adventure, whatever it is, right? Great. So we have like this sort of values for this, right? Recommended system. Now this is the Avengers movie you have been watching. It can happen that it can happen for sure. Now depending on that, it will basically check like, okay, these are our values, and depending on that, this guy is watching this movie, so I'm going to suggest him or her some sort of movie which has lots of similarity between this and the movie I am suggesting. So this is how the cosine, like cos similarity, can work on, right? This is exactly something we have mentioned earlier. So this might be some sort of movie X, and the cosine will work here, cos theta, and the things and value and others, and this is the dot product. So using that, we can easily understand like, okay, if the value is very near, we will get some sort of value and others, and it basically uses this mathematics, you see. So the cosine similarity works with the basically, obviously you were obviously doing the dot product here, and then the multiplication of the values, individual values. Okay, that's great. We've just learned about it, and there are lots of things we can work on, right? Okay, again, the vector databases can help, and the RAG system, I mentioned that, right? Now let's talk about the matrices. It's better, right? Let's start about it. So in the matrices are in general represented something like this. It's a bigger version of vector in general. You see, maybe it's a11, it's a21, and something it can be a m1, right? And it's a12, a22, am2, and it can happen, and it's, sorry, I'm saying a, yeah, it's a, obviously it's a1n, great, and a2n, amn, right? So what are these? One is this, you see, row 1 column 1, right? And this is row 1 column 2, right? So it's row 1 column n. We don't know how much columns we have like n number of columns, and we have m number of rows, right? So this kind of things are actually something like matrices. Okay, great. Now matrices, it can be like this is good, right? Because you see there are lots of big basically big data we can actually use the matrices for that, right? That's great. Now vector and matrices, there are few limitations and obviously the connections and so on. You can just learn about it when you learn the linear algebra, but my main goal is to like make you understand what are the user cases. This is much more where I'm interested in, where the mathematics, what kind of mathematics are used, or where are we using that, rather than explaining the maths deeply. This is because I've seen folks learning from mathematics for machine learning courses, and what they've been doing, and they've become bored after a while, because yeah, they have been learning this mathematics in their CS courses or from YouTube and as well. They just want to know where are we using that. So this is something we can actually focus on. Okay, so something like in a data set, if we have a data set right now, we have just mentioned it earlier as well, like for example, you have a math score, you have your physics score, and you have maybe your biology score, and it's about like 55, 65 is for 3 students, for example, 60, and 65 is 60, and it's 45, and for the biology it is 75, is 55, and it's maybe 80. So this kind of things, and we're doing that. Great. Now we can just represent this easily in a 3 by 3 matrix. Easy, right? We have been doing that for a while. It's 55, 65, 70, great. You can easily represent that. Just work with it. Great. So now the question might arrive, where do we use it? Images in computer vision. In the computer vision, again, the vectors, you see, that can be said like, we can easily say the image is something. For example, we have an image, the pixel is like, for example, the pixel values are 0, 255, 128, 255, and 128, 0, and 255, and 128, or something like that. Okay, what's the difference between vector and this thing? Just understand this properly. In the vector, just let me just write it better. Images. Okay, earlier what we did is, for the red color we mentioned maybe 255, 128, 0. For the green we also mentioned something, 3 values. For blue we also mentioned 3 values. But this was done in vector, right? Now, but in matrices, what we do, we just use all of these 3 values and create one thing, one entity, and I can just use all of the 3 right now. We just don't need to use those individually, right? So maybe, I'm not sure about it, but the values we can just easily RGB, right? You can just easily input them, 255, 128, 0, and then this, this, right? This was individual one, but this one is 3 into 3 matrix. It's easy. We're just representing it much more, and it is giving us much more access, right? Bigger data. Also, there's some things called confusion matrix. When you're working with the results of your model and something, you will learn about this confusion matrix. And if you talk about confusion matrix, great. Like for example, when you are inputting some sort of data, F1, F2 in our model, we're just getting some sort of output. Okay, great. And then we're passing this and we're getting some predicted output and so on. Basically, this is how things work. Now, the thing is, in confusion matrix is something, a matrix, for example, you will see, for example, you have 50, 10, 5, 35. Okay. And for example, I have mentioned earlier the dogs and cat example. We've just provided that, you're just using that and to try to see, like, okay, if the model can learn whether a image is dog's image or cat image, right? There are a few things that happens here. So there is something called, this 50 is basically a true positive value. That means, okay, it has successfully understood what the thing should be, true positive value. Okay, there are other things we do have, and that is, this is true negative value. This and there are another few, like this 10 is basically true negative, and this 10 is basically false negative. This 5 can be false positive. Now the assignment for you guys is to let me know in the comment section what these are, Fn, Tn and Fp. But why are we bothered about confusion matrix? Because if you have worked with machine learning, if your friend have worked with machine learning, whatever it is, they might have talked about accuracy. So how do we define accuracy? The accuracy of something is basically coming from these things like TP and TN. These two, we are just summing up these two and dividing it by everything we have, like 50 plus 10 plus 5 plus 35, whatever he has. We have all of the value. I'm just defining that, and we get some sort of value. Now, if we have a value accuracy of like maybe 0.9, this means 90% accuracy. So our main goal remains to increase the accuracy. So you see, the confusion matrix is something we do create, and with the using that, we just then get the value of accuracy. So it's very much something interesting. And also in the neural network, we have again earlier talked about the vector or linear. So this is exactly the same thing. It's important to understand the matrix addition and subtraction. You need to know about it. So it's your task, homework, I would say. This is how a matrix addition and subtraction. This is how you just will learn it, and it's very easy. Just check any video. And also matrix multiplication. Okay, matrix multiplication. That's great. Now we'll talk about functions, and functions are going to be something. There's a last topic for this video. So functions. So what are functions in general? Okay, assume that you have a range of input values, right? And this can be some sort of real values, and I'm assuming you know about real values, and you have some sort of range. This is basically called domain, like the limit for us, or this is allocated for us, which we use and input it within some sort of thing, maybe called function, and we get something called codomain. And it can be something like the real values as well. Now, for example, it is 2, the domain can be 2, 3, 4, and the codomain can be 5 like 9 8 something. Now how do we get domains from codomain? That's interesting. And the ranges are in general, like we have all the values of codomain out here for sure, like 5 9 8, and we do have more data like maybe 16 19 or something, and this is the range. Okay, great, no problem with that. So how do we define the notion? We basically define by f, so is that x maps to y. It is for now, let me give you some sort of example out here. Okay, example, like for example, we have something called 2x plus 3, a linear algebra linear equation. You can just easily say that, right? For assume that the fx equal 2x plus 3. So what is this fx? So this is how things do work. So for a value of x, use this equation to get a value of y, right? Simple as that. So fx, so for example, if we are provided with a value x equal 5, which is maybe part of our domain, and just for this example maybe 2, if you just use 2, better, it's better to understand. Not sure if we'll get the value. Okay, 2, and then fx, which actually means y, is equal to 2 into 2 plus 3, which is 7, right? Which we don't have here, right? Let me just remove these 5 and this 5 as well and write 7, no problem with that. This is exactly the same concept basically, but right now we have some sort of equation which I didn't have earlier. I just made some sort of value. So this is how things do work. So this is our domain, this is our D domain, and this is our codomain. And ranges is basically, ranges are mentioned like, okay, this should be the range. Codomain are part of the range in general. Great. So this is the thing. Now what can we do with it? Vector transformation. This is we are learning the, what I would say, we're learning the functions, right? Now there can be some functions you can consider them as some sort of equations or some sort of black box. All right, we are just consider them as black box for now. For vector transformation, we can just use them. Transformation, we put some sort of vectors out here, we get some sort of vectors out here. Now you'll say like, okay, why is it important? For example, if you're passing a vector of value 1 2 3, it's a column matrix, or you can call it a vector. Matrix and vectors are almost the same, they mean, and you are getting a value, you see, you're getting a value of 3 and 6. Now you can say like, okay, this is something 3-dimensional, 3 values, right? 3D, and we are getting 2D. That's interesting, right? This is something we have talked earlier as well, the dimensionality reduction, right? And we are basically passing these value through a function for sure, right? We're passing through a function or something like that. We're getting this. This is how things do work. The vector transformation happens like that. Okay, so the image can be something like this, can be 3D and 1 2 3. This can be the point 1 2 3, and we just transform these to 2D, and within that maybe this is the value 3 6, right? So we're transforming this value to this, we're making this value to this, and this was a 3-dimensional value, and this is a 2-dimensional. We using the function, we have just done that. So this is something, and we can also do the scaling here. Scaling is a transformation that changes the magnitude of vector. Okay, so some sort of for example, we have a vector of 2 3, or you can call them matrix, no problem with that, but vector is better. So it's a vector, and we're just multiplicating 2 with it. It's like 4 6, right? So this is scaling. Now visually it is like, for example, it was 2 3 here, The 4 6 surely will be in this same line as well. 4 6 and this is 2 3. That's interesting, right? You're just scaling the value, right? And I should not actually add this line, this more, sorry. I should be adding this only from this to this, like it was earlier 2 3 here, so this line, and then it increased to this, so it's down 4 6, so we can scale it up. And now we can say, like, why do we use that? In general, in the data normalization or computer graphics, we do use that, because you see, we'll talk about normalization later on, but in the computer graphics, what happens is, I mentioned earlier as well, like sometimes you might need to like grayscale the image, or sometimes you need to make some sort of rotation, whatever it is, for the pixels and others. You just scale it up or scale it down, no problem. It is now scaling, we have scaled it up right now, right? But whatever, when if we would have like used like -2 here, it would have been -4 -6, so it would have scaled down, right? Minus values, right? That's interesting. And for the rotation and others, we can also do these things. For the reflections, we can use that. Now the linear transformation is something that's very important for us. We just talk about the transformation, vector transformation or something. The linear transformation, this concept is something I'm totally giving it up to you, like, okay, linear transformation, something you need to learn. I will show some example and tell you what this is, linear transformation. So what it is, linear transformation is basically a function between two vector spaces that preserves the operation of a vector addition and scalar multiplication. So we have just talked about the scaling, right? And also preserve the operation of vector addition, so, and the scaling multiplication. This means that T is a linear transformation from a vector space V to a vector space W. You see, so linear transformation, again, this thing is related to our function concept as well. So this is a transformation which actually follows that it preserves the operation of the vector additions. What is vector addition? If we have two vectors and if we just add them up, we should have this thing as well, TU, and if we just individually add them, we should get this. It is basically called additivity. Okay, so this the linear transformation basically preserves this thing, and again, homogeneity, homogeneity. So we have something like that, whatever people do call it. Now you see, we have some sort of scaling value and maybe a vector. Now we can just call it this vector, so it just makes it better. If you just do it, it should have T. Okay, it should be something like that. C is a scalar value here, so it preserves two things. One is, you should be able to actually add the or you should have the additivity of the vectors. You should have this principle for a vector if we have that, and also the homogeneity. So if we have both of these things, you can call anything a linear transformation. This is great. Now, for example, I'm just going to give you one of the examples, and that is reflection. For example, reflection. Okay, assume that the reflection transformation should, like, for example, you have x and say x, y, and the values are the R space 2D, and you have a tx which is minus xy. It gives, if you pass xy, you get minus xy, no problem with that. And it's basically a linear transformation T across the y-axis. Now if you just visualize it, it is very easy. You see, if this is x, y, right, then this is x, right, xy, and then if we have another point, it is minus xy. So across the y-axis, because of the y-axis, now they have the reflection. This was the point earlier, and this is the point, you know, that's just like a mirror, right? You can call it a mirror. My drawings are so bad, nothing to say. Okay, so we can just call it a mirror, something like this, just mirror or something like that. And you see, there are two sides of it. So it's just for the reflection, right? So transformation can be explained as a equal, like for example minus 1 0 0 1, right? For example, if we have tx and if we now provide tx, yeah, maybe it can happen. We have 1, right? No problem with that. Sorry, we have a, right? Great. So if we had just earlier, if we just look into x, we have xy, right? Now this tx, we also know the value should be minus xy to get the transformation reflection. But how do we get it? In general, what happens is this tx is basically something like we multiply like xa. So x is something we had xy, and the a was something like minus 1 0 0 1. If we just multiply the matrix multiplication, you will see that you will get the value minus xy, which is exactly the value of tx. Okay, so this is what, that's very important to understand. Like this is something that should be given and that should be known. This is something there are lots of value for this kind of matrices. Using that we do get like okay, whether how to get this kind of thing or this kind of things. Okay, now what you can do, the homework for you would be to let me know if this is linear transformation or not. To know if this is linear transformation or not, I'm just going to give you an example. I will show. There are two parts, right? First of all, you need to ensure if this is if this follows the additivity. What is the additivity we have mentioned? We have mentioned if u plus vt tu, sorry, plus tv. Okay, these are our vectors. So this is our target. Okay, now for example, this is what I'm going to show you, but what your responsibility is to know or let me know by this if this follows this one or not. Okay, okay, so tuv. Okay, so what we can do is, assuming that u equal u1 u2 and v equal can be v1 v2, no problem with that. Great. Then u plus v is something like u1 u2 plus v1 v2, and we get something like u1 plus v1 u2 plus v2. Great, we just get that. Then t u plus v should be something like basically applying t is something here the matrix we have been provided, right? So it can be something like this. T can be say minus 1 0 0 1, and we just multiply with our uv, which we got u1 plus v1 u2 plus v2, and we can just get that. We just use this one and using that we may get some value. Just so it's just minus 1, right? So it should be minus u1 minus v1, and there should be u2. Obviously it's you see these are just like the addition, right? And this is like now we have v2 plus v2. Okay, great. Okay, now we're just done with tuv. Now we have to do this one, tu, or we can call it au. We have a, right? Or you could have called it tu as au plus v. Okay, call it. And this is what we did. This was our a and au, right? So we have a. So we just do it minus 1 0 0 1, and we just do it, and we just get u1 u2, and we get it something like minus u1 u2. Great. And talking about tv, same. It can be said as av or something, and a has the value minus 1 0 0 1, and the v has v1 v2, and we'll get something like minus v1 v2. Now if we add tu plus t2 v, we will surely get, you can easily understand from now on, that is this should return us minus u1 minus u2 v1 plus v2, and this is exactly the same thing we had in tu plus v. Now the game changer or the main difference is basically this a. If this matrix was something, not this one, because this is one of the matrices which gives us linear transformation. If we had different thing, maybe instead of 0 it was 7, or instead of 0 is 2 or something, it will never come this kind of thing. We will never have this kind of thing. So you can see we have a applied everywhere. Applied everywhere. So yeah, this is how. So this is the main game changer, and depending on this matrix, it actually was a linear transformation or not, I don't know. I think it should be linear transformation. It should have the linear transformation, but you have the responsibility to let me know if this fulfills this this one as well. This is your homework, to let me know in the comment section, hey, it just fulfills this one, and so we can call it a linear transformation. Okay, now you can say like, why are we bothered about linear transformation? Because earlier you see everything is connected. So the linear transformation, we have basically PCA, which is basically principal component analysis, which is used in dimensional reduction. So we basically use these things. The PCA, for example, we have 5,000 data. We just use the PCA information, and we'll just get some sort of data which is very different, very less, like maybe 200. We just limit that 500 dimensional data. We just reduce that. We'll just understand when we work with our coding problems. And for we also use it in our feature engineering. We use it in our feature engineering. We also use it in data pre-processing. And so on, just more. And we also use it in our neural networks, linear transformation. We use it in our image processing, robustness, stability, geometric interpolation, and so on. But for the last topic for this video should be the inversion or inverse of a function, to know about it. For example, we just have learned about x, f, and y. We just have learned about it, like we just follow this one and what if we just have y but we just want to know about the x? This is the thing, this is the reverse of the thing. All right, now you may say like, why should we know about the inverse of a function? That is very that is something you can say, for example, right? Interesting. Let me just give you an example. For example, we have we started with one of this example, the area and number of rooms, and maybe the location and the price. The area should be like, we have 1,500 maybe, and maybe 1,800, and number of rooms 4, 5, and the location 1 and 2, and it is 5 CR. It should be 6 CR, 1,800, right? Okay, no problem with that. Now you see what is important for us to understand, that is the values are big. It might be like 1,500. No problem. It's not that big. But what like, we surely don't have like 2 data only for 2 house, right? We will have lots of data, maybe thousands of data or millions. We can have that for sure. So if the values are 1,500 each time, like obviously the multiplication will take time. And now it's important to understand that is we are using GPU or CPU, right? Mostly the GPUs. Obviously our target is to use it for the less period of time. The more we use it in cloud or in our local system, it costs or hit much more hotter, right? So it's our responsibility, or it is our target to like, okay, reduce the time or something like that. Great. So this is what we do, is we do normalization. So how do we do that? That's interesting. For example, the number of rooms, if we just consider this as a vector, there are other loss of data. This can be vector, this can be vector, and all as well. Through some sort of process like the function, through some sort of like a process, what we can do is we can just make this data something like this. Maybe call it like maybe what we can do like 1 2 3 4. Like for example, we have just 4 data: 1500, 1800, 2000 and 2400, using some sort of function or something. Our main target is to keep it very low. It's better to keep it within 0 to like 1 or something, but yeah, for example, we have just done that. We can do that for sure. So we can just make it small, right? Smaller. We can also make it like 4 to 5 and others to very small values. And what will happen is the multiplication and others will take less time because the values are small, right? This is how we do it. Now the problem is not this. The thing is why we are talking about the inversion, right? Talking about the inversion is a bit different concept because, for example, using the small values, you have now defined, you have got a result, right? We have trained the function and so on. Now what if you want to know, you want to get it back, like for the information like it is maybe for 2400 and this is maybe for 9 and this is location maybe 6, and we have got some sort of price and so on, maybe 9, but these values have been like the area we have you have made it like maybe 4 or something like that. The value we have just normalized it and made it very small. We can just do that. We made it smaller. Now what if now what we have to do is we have to use the inverse function again. We have used some sort of function to make it smaller, then we will use the function again, inverse function f inverse 1x, to get the value, right? So we now know, like for the 4 we have 2400, so we just use the inverse function out here. So there are a lot of things here, mean, standard variation and so on. You just need to learn about it. So your task should be again to learn about the Algebra, should be to learn about the standard deviation, because we will talk about it in our statistics part later on. Standard and deviation and mean, right? These kind of things. Okay, so yeah, that should be it for this video, I believe. And thank you so much for watching this video. If you had any questions, my main goal was to make you understand, okay, vector, matrices, functions, these are somehow working in machine learning or somehow used in machine learning, and where is it getting used? Because sometimes many folks start learning machine learning prior to learning the mathematics, because they might have learned this mathematics concept in their colleges, and they don't bother about it that much more, and they start learning. So but later on, for the research purpose, when you are reading the papers, you will understand there are a lot of things that is introduced, but you don't understand that much, because you don't know where the mathematical concept was used. Rather, you just know how to use the library. So if you know, like, okay, the principal component analysis, or this kind of things used in this in the linear regression, how you deal with the matrices, or where the matrices is coming from, or how the data is represented, this kind of things you can easily understand. Okay, we can relate this, you can do the good research, right? So yeah, that is the main goal of our session. Okay, so this video was actually created on that. And yeah, thank you so much for watching this video, and I hope to see you in a next video.